Let's do another example of calculating moments, but this time we have a little bit of a tricky situation. It's kind of hard to see, but we have this member that has point A, B, C, D, and E. The force being applied at B is actually at an angle of 30 degrees, but then we have a force being applied at C, just straight across, and a force being applied up at D. And then we have our dimensions here. So it's asking, we're being asked to find the force or the moment being created by the force at C about point B, the moment being created by the force at D about point A, and the moment being created by the force at B about point C. So let's start by, we would draw a free body diagram, and you would remove these supports, but we're just going to go straight to calculating the moments. So if we're being asked to find the moment, we're just going to calculate the magnitude of the moment about point B caused by the force at C. So we take the magnitude at C times the perpendicular distance between B, which is our point of origin, and C, the point of application. We take then our force at C, which is 90 newtons, times the perpendicular distance between B and C. So B to C, this would be our perpendicular distance, which is 160 plus 120. Can't probably see that very well, but that's what it is. So 280 millimeters, which is then equal to 25,200 Newton millimeters. But we typically do the unit system for SI as Newton meters, so we convert that to 25.2 Newton meters. And to find the direction, make sure we tell which direction the moment is going. We put our finger at the point of application and apply the load to the member, and you can visualize then that it's going to turn in the counterclockwise direction. Then for B, we need to know the moment created about A caused by the force being applied at D. So we multiply the magnitude of the force at D times the perpendicular distance between A and D. So the force at D is 120 newtons, and the perpendicular distance between A and D is that pink highlight. So that total distance is 550 millimeters. So from there we get 66,000 Newton millimeters. And converting it to Newton meters, we have 66.0 Newton meters. And we have to figure out what direction that is, so we're doing it at point A and applying the load at D, so it's going to cause a counterclockwise rotation. Finally, we're looking at the moment about C caused by the load applied at B. So we multiply the magnitude of the force that will cause the rotation at B times the perpendicular distance between C and B. So now this one's a little bit trickier because FB is at an angle. So the only component of that force, so if we were to take that force and look at the components of that force, we have the component that will go in the X direction and the component that will go in the Y direction. the component in the x direction is perpendicular to C, so it will cause a rotation, but the component in the y direction is parallel to C. So if you pull on that, it's not going to cause any rotation. So the only thing we need to worry about here is the component in the x direction. So we can take the magnitude of B, magnitude of the force at B, 150 newtons, times the cosine of 30 degrees to get the x component of that force. Oh, I already had newtons. And then we can multiply then by the perpendicular distance between C and B. Which will be 280 millimeters. So that is equal to 36,373 Newton millimeters, and converting that we get 36.4 Newton meters. And then to figure out what direction that is, we put our finger at C and apply the load. That, just looking at that perpendicular, we would apply the load. So it's going to make the member spin in the clockwise direction.